All right, fam, we are on section 12.1. This is our very last chapter. This is the day one of this chapter. And what the good news is that this really reviews a bunch of stuff from chapter 3. So as you can see, I have this whole thing already filled out. So if I go too fast, I'm not trying to make some long ass video, okay? Pause it and copy down, and don't come at me about talking too fast, okay? Here's what I want to first kind of go through. This is an interesting problem because I wonder if you guys think that the row you sit in has any sort of correlation between your score on a given test, because that's what the wording up here is talking about. Let's look at our students that are sitting in the front row. And these students were randomly assigned to the front row, 76, 77, 94, 99. Let's look at the back row, 79, 76, 77, 63. Here is a scatter plot of this data. There are 30 students here that participated in this experiment. This teacher randomly assigned the students to seat locations, okay? And here's what our scatter plot looks like. You remember how to like describe a scatter plot, like moderate, weak, strong, linear, positive, negative, quadratic, that kind of thing. I'm going to go through these one at a time, but a bunch of this is going to be review from chapter 3, okay? But letter A, the question being asked about is causation. What allows us to conclude causation, and what about generalizing to a population? This is chapter 4, BT dubs. So just remember that in order to use the word cause in stats, we must have random assignment within our experiment, which we did. We randomly assigned our students to rows, okay? And then generalizing, in order to generalize to a broader population, which right here, I just have my own students, let's see, in my classroom or in this teacher's classroom. So I didn't randomly select them, but only if you have a random sample, random selection, are you allowed to generalize to a broader population wherever your sample comes from. Okay, do you remember how to write the sentence for the slope? And by the way, here's our equation. Do you remember like the y hat situation? So the score is the y hat. We have 86 minus 1.12x. The x is the row number. The row explains the score. Remember that the x planetary variable always goes on the x-axis, explanatory x-axis. Anyways, so do you remember how to write the sentence for the slope? Because here's what it looks like for every single additional, or another word of saying that is as we increase whatever the x value is, which in this case is the row. Important word, expect or predict the y value, which in this case is score. To increase or decrease, in this case we have a negative slope, it's right here. To decrease by about, the slope is 1.12, and the units on that is points. What that means is if I force a student to move back, I expect their score to go down by about 1 point. Do you think that's significant on a test? 1 point? Maybe, maybe not. Okay, anyways, does the negative slope here, this is negative. Do you think if I would have done a different sample, or if I would have reassigned all of these students to different rows, I would have still gotten a negative slope? Do you think there's any way that if I reassigned all these students, I would have gotten a positive slope? Because probably. But what this question is asking us to refer to is this 100 different dots up here. We had a computer program reorganize all of these people into different rows 100 different times and calculate the slope for all of those different scatter plots. And what we have here is a dot plot of all the different slopes. As you can see, zero's right in the middle. We have some negative slopes. We do have some positive slopes. But because our slope of 1.12 is about right here, negative 1.12, and I'm counting roughly 11 dots that are at that value or even more extreme. Think about p-values. Our p-value here would be 11 out of the 100 dots. It says there's 100 dots right here, so I know there's 100. And so I think that it's possible that this association is just due to chance. I don't think it's always going to be negative. I think that this p-value being 11% is not low enough to make me think that the slope would always be negative. Kind of think about that's where we're heading in this chapter, okay? So think about p-values. The 11% isn't considered that uncommon, okay? What you should have read about in your reading guide is the 5 conditions. Yes, there are 5 for this chapter. And I know that really sucks to think about, but, and I know this looks like a lot of words, but pay attention instead of feverishly copying down. Let me explain these. Here's your acronym. We are in a linear regression chapter, and our acronym for our, what's it called, conditions are LINER. Isn't that kind of cool? So the L stands for linear. And is it okay that we refer to this scatter plot as linear as opposed to quadratic, exponential, anything else? Yeah, it is a weak correlation, but I do believe I would use the word linear to describe it because I am not seeing any other type of shape that I can recognize, okay? So for reason number 1, the original scatter plot shows a weak negative linear relationship between the x and the y, the test score and the row. And do you remember what a residual plot is supposed to look like? It's supposed to be a consistent random scatter. Do you remember this from chapter 3? Think StatsGetBall. We did a ton of writing and stuff like this in chapter 3, okay? The I stands for independent. Each student's score, it's reasonable to believe, is independent of each other's. Notice I'm not checking the 10% condition here because this is an experiment. I did not take a sample of students. I just forced my students all to participate in this experiment. I would check the 10% condition if I took a random sample, which in this example, read the wording way at the top, I did not take a random sample. I just used all my stats students. The N stands for normal. So look at this residual plot right here. It's a histogram, and the histogram of the residuals looks normal-ish. Remember, it's never going to be perfectly, beautifully normal, but I believe it's okay to refer to this as approximately normal. And do you remember this thing right here? It's called a normal probability plot, and it's supposed to be roughly linear, so there we go. As you're copying down, yes, you're given a lot of stuff here, and yes, I'm mentioning a lot of things. Here's the way to try and get a 5 on the AP and get bumped up and not bumped down if you're in between scores. If they give you a residual plot that's a histogram, then mention it somewhere, okay? They're testing you to see if you know what this is supposed to look like. Do you know what this is called? It's a normal probability plot. Do you know what it's supposed to look like? It's supposed to be linear. If you know that, you should communicate that on your AP exam. So here's your chance. I'm just putting it in the notes. These are all the different kinds of things you might be given to help you with the conditions, okay? Equal variance. That is kind of new. And equal variance, I think you probably remember. Let me kind of draw a sketch. I drew this on the board in class. Do you remember when we were doing our StatsGetBall residual plots and we had some residuals that started out really small and then they gradually got way bigger? Do you remember how that was like bad? Do you remember how that meant that our predictions were pretty good? Our residuals were very small. That means the difference between the actual and the predicted value, the residuals. The residuals are pretty small at the beginning, but then they start to really skyrocket. That means we're not very accurate for larger values of x. Okay, that is an example of not having equal variance. And I've also seen the flip side where you start out really sucking at your predictions and then gradually you get better and better and better. Okay, this is another example of not equal variance, okay? We have large residuals followed by small ones. That's what you're checking for, excuse me, to pass the equal variance condition. Here it is. This residual plot does not look like either of those that I drew. This looks like it has a completely random scatter, and the residuals do not increase or decrease as x increases. So equal variance, I think, is good. And last but not least, usually we do this first, but because it makes an acronym called LINER, we're going to do random last. We have randomly assigned treatments. Don't just say random check. Say what is random about this, in this case, experiment, and we have randomly assigned the row numbers to the students, okay? Now, do you remember a regression output? So yes, we already know this equation. I wrote it on the front page, but do you remember where to find these things? This is your y-intercept. This is your slope. And remember, define any variables being used. Some of us don't like to read all the directions in a problem, so make sure that you define your variables always. We already interpreted the slope. Do you remember how to interpret the y-intercept? That means when you plug in 0 for x. What is x again? It's the row number. Okay, so row 0, is there a row 0? No. The front row is considered row 1. And remember that sometimes a y-intercept having an x value of 0 does not make sense in context. The example we did in class in chapter 3 where it did make sense to plug in 0 for x was we were predicting the weight of a rat based on how many weeks old it was. And when you plug in 0 weeks to the equation, that means that when the rat is born, it is 0 weeks old. That actually did make sense in context. This one doesn't make sense because we don't have a row 0. Moving on. Here's something new and fun, maybe. Another number from this regression output, this SE sub B, this number. You need to know that. I don't think we've ever talked about that before. SE sub B means that on average, the slopes of the sample regression lines differ from the true slope of the population regression line by about this much. What does that mean? Remember this dot plot up here where we like rearranged all of these people 100 different times using a computer generated situation, and we came up with this dot plot of 100 different slopes. So we're using this to estimate what the true slope of the entire population would be, which you know would be really difficult to come up with. But if we, let's see, if we do all of those sample regression lines, they would differ from the actual slope I'm trying to predict by about this much. That is what the SE sub B means. Okay. Last thing to wrap up, you guys. Finally, after getting through all of that and doing so much review, we now have to calculate a 95% confidence interval for the true slope. So here's what we're going to do. I already wrote my conclusion sentence. I'm not really sure why I wrote it first, but how do I get this interval? Let me show you. Do you remember the formula in words on the formula sheet for an interval? We are trying to estimate the true slope. We did an experiment one time and we got this slope to be this number, but what if I did it again? Would it be this number? We don't know. We're trying to decide if it's going to be positive, negative, 0. We don't know. That's what we're trying to estimate. We only did it one time, and this is our current slope. So let me go to the end. Our statistic in this case is going to be the B, the slope of our sample regression line from the first page. The critical value is do you know? It's a T star always for this chapter. And the standard deviation of the statistic, this is very exciting, is the SE sub B. Yes, this number that I just talked about. So let's plug all that stuff in. Do you remember that the slope from the front page of the scatter plot at the very top, the slope was negative 1.12? I'm going to leave that T star for a second, and I'm going to plug in everything else I know. The SE sub B is this number from the regression output. Remember, it's from right here, 0.9472. And how to find the inverse T. So inverse T, let's see, for a 95% confidence interval, that means I have 2.5% on each tail. And the degrees of freedom in this chapter, and this is the only chapter where this happens, is n minus 2, which is 30 minus 2, which is 28. The way I remind myself that this is the only chapter where degrees of freedom is n minus 2 is because we're measuring an x and a y variable. We have two variables to take into account, and for some reason that sticks in my head, and that's why in my head it's n minus 2. There's a fancier mathematical reason for that. We don't need to worry about that. When I do inverse t in my calculator with this degrees of freedom, my t star ends up being 2.0484. Check me on that if you want to. And now I just crunch this, and I end up with this interval. So here's the deal. What does that interval tell us? Do you remember when we calculate an interval and we're estimating something, if there are both negative numbers and positive numbers in there, that basically is inconclusive? I am saying that if I do this scatter plot, the slope could be positive, the slope could be negative, and the slope also could be 0. I have no idea. So does that mean some of you should move up? No. We do not have a useful linear relationship between these two variables. Good for you who are sitting in the back. You may stay. There's your day one, you guys. Ask me some questions in class, okay? Thanks for watching.